Hello, this is FASTECH. Until now, it has been taken for granted that AC servos performance is superior to stepping motors. However, Ezi-SERVO raises the position accuracy of stepping motors through high-resolution encoders, and takes advantage of the characteristics of stepping motors that AC servos cannot have, allowing them to have the same or better performance as AC servos in some applications. I will explain in detail now. First of all, I will explain how the position of AC servo and stepping motor is formed in the current Korean market through market segmentation. This is the data only for the Korean market. The horizontal axis is performance, and the vertical axis is cost. Existing open-loop stepping motors were recognized as low cost and low performance, and the AC servo is a high-performance, high-cost motor. And the location of the closed-loop stepping motor was here. It is a common perception of customers that it is better in performance than open-loop stepping motors and lower than AC servo motors. In this market, competitors' closed-loop stepping motors have been dominating the Korean market for about 15 years at twice the price of AC servos with two advantages: no hunting, and shorter settling. In addition to these two advantages, FASTECH moved the market from here to here with another advantage: high position accuracy, and achieved the #1 market share in the Korean stepping motor market. From now on, let's compare these three advantages: no hunting, short settling time, and positioning accuracy between Ezi-SERVO and AC servo with laser demonstration jigs. The terms to compares are position accuracy and lost motion, related to position accuracy, comparison of settling time according to OverShoot and OverShoot related to short settling time, and robustness related to no hunting. We have prepared demonstration jigs to compare the two motors in these 5 aspects and see the difference in performance. First, let me explain the specifications of the demonstration. As you can see, there is a demonstration in which you can visually observe the movement of the motor shaft by attaching a mirror to the motor shaft and reflecting the laser point on the screen. The measurement conditions for both motors are the same. The size of the Ezi-SERVO motor is 42 mm, and the resolution of the installed encoder is 10,000 ppr. The capacity of the AC servo is 100 watt, and the resolution is also set to 10,000 ppr. The distance between the demonstration jig and the wall is 8.4 meters. First, let's compare the position accuracy of the two motors. As mentioned earlier, the measurement conditions for both motors are the same. Both motors were made to move at equal intervals by 0.36 degrees in only one direction. At this time, let's compare whether the actual position comes the same. As you can see, the AC servo has a constant moving distance at equal intervals, so it has high position accuracy without any position error. One thing to note is the Ezi-SERVO. Even though it is a stepping motor, you can see that it has the same high position accuracy as an AC servo. Good position accuracy means that when it is moved in one direction, it does not show position error like AC servo and Ezi-SERVO. Next, let's compare the lost motion. The measurement conditions were the same as before. The difference from position accuracy we saw earlier is that the motor rotates alternately in the CW and CCW directions by 360 degrees. That is, in the case of lost motion, the direction has to be changed. As you can see, the AC servo rotates 360 degrees regardless of the direction, and it returns to the target position without any position error. Likewise, even if the direction of the Ezi-SERVO is changed, you can see that it returns to the target position without any position error. Lost motion refers to the position error that occurs when the direction changes. In summary, position accuracy and lost motion are related only to the accuracy of the encoder. An Ezi-SERVO uses a high-precision encoder like AC servos, so it always checks the current actual position and corrects it so that there is no position error. Thus, Ezi-SERVO has high position accuracy and small lost motion. Next, I will show you the overshoot. Overshoot means the value of how far the motor has exceeded the target position. The demonstration used the same demonstration as before. From now on, let's see how the overshoot differs when the motors are moved under these conditions. As you can see, Ezi-SERVO has a small overshoot, but AC servo has a relatively large overshoot. Of course, the AC servo used in the demonstration is not optimal because it has been tuned with the auto-tuning function, and overshoot can be reduced if it goes through a precise tuning process. But even without such hassle, Ezi-SERVO can show its performance without overshoot. This overshoot will affect the settling time. I will show the difference in settling time according to the overshoot in a video. We set the in-position value to 0, which is the condition that the next command is executed only when the commanded position is reached without an error of 1 pulse. Repeated operation 50 times without waiting time between commands. As you can see, Ezi-SERVO with less overshoot completed 50 repetitions about 4 seconds before AC servo. If the larger overshoot occurs, more time is required to execute the next command. In other words, the takt time would increase. That is why short settling times are important. Finally, let's compare robustness. Let me show you what happens when the same external force is applied to the mirror on both motors. Ezi-SERVO does not move much even when external force is applied. Whereas AC servo shakes greatly, that is, hunting occurs. This will be explained in more detail through a comparison of the torque characteristics of AC servo and Ezi-SERVO and a demonstration video later. Before that, I would like to ask you a question with a real machine as an example. This application is the XY theta vision alignment stage, one of the most common applications. Basically, alignment is a machine that allows the camera to accurately capture the object to be inspected by continuously moving a short distance. In this machine, a 100-watt AC servo is mounted on the right, and an Ezi-SERVO of the same size is mounted on the left. Would AC servo be better for this application? Or Ezi-SERVO be better? Customers have taken it for granted to use AC servos in applications requiring high position accuracy. As mentioned earlier in the market segmentation, customers generally have a perception that AC servo performance is better than stepping motor. Of course, the correct answer is Ezi-SERVO. But the why is important. How can a stepping motor show better performance than an AC servo? We will explain it in the next chapter. First, I will explain the difference between AC servo and stepping motor with torque comparison. Let's compare the torque of similar size AC servo motor and stepping motor. The graph shown above is the torque graph of 200-watt AC servo motor, and the graph below is the torque graph of Ezi-SERVO of the same size as 56L. First, AC servo motor has two kinds of torques. A rated torque, and an instantaneous torque, which is 3 times higher than the rated torque. On the other hand, stepping motors have a holding torque. Not the rated and instantaneous torque. That gives maximum torque when the speed is 0. That is, when the motor is stopped at the target position. Simplifying this, the rated torque of the AC servo motor is 1. The instantaneous torque is 3. And the holding torque of the stepping motor can be standardized to 2. Even if this is applied compared to the 100-watt class of AC servo motor and 42 mm stepping motor of similar size, the torque value would be different. But the ratio of rated torque, holding torque and instantaneous torque is always the same as 1 to 2 to 3. And AC servo motor has higher torque than stepping motor because of this instantaneous torque of 3. Since the instantaneous torque of the AC servo motor is 3 and the holding torque of the stepping motor is 2, the torque of the stepping motor is smaller than that of the AC servo motor. But the important thing here is that the instantaneous torque is not always usable torque. There are limitations. If this instantaneous torque of 3 is always used, overcurrent and overload alarms are likely to occur in the AC servo drive. For example, if you perform rapid acceleration-deceleration using instantaneous torque of 3, the torque is proportional to the current. So if you use this torque for a long time, the coil inside the motor may burn out. It triggers an alarm. Literally instantaneous, that is, it is this instantaneous torque that can be used only for a while during acceleration and deceleration. Also, even if an instantaneous torque of 3 can be used, when the speed is 0, that is, when it is at the target position. The stepping motor has a higher torque than the AC servo motor because of the holding torque of 2. As previously explained, the instantaneous torque of 3 is not always used, but the torque of the AC servo motor is proportional to the position error. The smaller the position error, the smaller the torque, and the smallest torque at stop, that is, at the target position. For example, as you saw in the toughness comparison video using the laser demonstration earlier, when a small mirror is attached to the motor shaft and touched by hand, the torque generated by the AC servo motor is very small because the positional error is small. Therefore, it is easy to rotate the mirror by hand at first, but as the mirror is rotated more and more, the positional error becomes larger and the AC servo supplies more current to the drive to reduce this position error. Thus, it becomes difficult to rotate the mirror. In other words, the torque of the AC servo motor is not always an instantaneous torque of 3, but is proportional to the position error and produces the smallest torque when it is at the target position. So there is a high possibility of hunting after stopping. Of course, if the gain is adjusted for the AC servo, the response improves as you can see. But when it is near the target position, you can see that the torque is the same regardless of the gain. On the other hand, since the torque of the stepping motor is not proportional to the position error, it is only related to the speed. and has a holding torque that produces the maximum torque when stopped. A possibility of hunting after stop is smaller than that of AC servo motor. Now let's divide the motion into two and compare it. One is a long pitch motion, in which there is a constant velocity section, and the other is a short pitch motion that decelerates immediately after acceleration. Now, let's assume that a certain load is accelerated and decelerated by A, using the instantaneous torque of 3 of the AC servo motor. Assuming that F equals ma, m, the load is a fixed value. First, in the case of a long pitch motion, acceleration is a when accelerating. Since there is no change in speed in the constant speed section, the acceleration of the load is 0. And the acceleration when decelerating is minus a. Therefore, the absolute value of acceleration-deceleration applied to the load, that is, the impulse, F, is a. On the other hand, in the case of short pitch motion, this constant velocity section does not exist, and deceleration is performed immediately after acceleration. In other words, since acceleration and deceleration change continuously, the amount of impulse applied to the load is 2a. To make it easier to understand, for example, if you use an instantaneous torque of 3 like an AC servo motor, you can understand that the shock transmitted to the vehicle body is doubled if you press the accelerator and brake continuously. Therefore, in short pitch motion, instantaneous torque of 3, that is, maximum torque of AC servo motor cannot be used. This is because if used, it is more likely to cause shock or vibration to the mechanical system, such as a car as an example. In order to reduce the shock or vibration of the mechanical system, the acceleration must be reduced. But to reduce this acceleration, the acceleration-deceleration time must be increased. This reduces the acceleration received by the load. And hopefully, if the torque drops to the point where it can accelerate with the torque of 2, which is the holding torque of the stepping motor, even if the AC servo motor has a maximum torque of 3, it cannot use this torque, and in this case, the AC servo motor, stepping motor, and torque become the same, and the acceleration capability is also the same. Back to the beginning, I will ask again. In short pitch motion applications that move short distances at high speed, such as the XY-theta alignment stage, when it is stopped at the target position and shock or vibration comes from outside, which motor of AC servo or stepping motor is likely to hunt? It's an AC servo. As mentioned earlier, if you use the instantaneous torque of 3 of the AC servo, it can give a shock to the mechanical system when aligning. Also, when aligning, the distance is very short, so it is often difficult to use an instantaneous torque of 3. First of all, as you saw in the video comparing the robustness of the laser demonstration, the AC servo generates the smallest torque when the target position, that is, when the speed is 0, so there is a high possibility of hunting after stopping. However, in the case of a stepping motor, there is a holding torque that exerts the greatest torque at the target position, so when the alignment is over, it stops at the target position and holds the stage tightly with the holding torque. This is demonstration of the difference between AC servo and Ezi-SERVO in the high-speed short-pitch motion, described so far. The same actuator with the belt structure is equipped with a 42 mm size Ezi-SERVO on the left, and a 100-watt class AC servo on the right. There are cameras on each side, and there is a piece of paper with a small word on it. as the camera moves by motor continuously over a short distance, that captures the written text. You can think of it as the same as a vision factor. As you can see, the Ezi-SERVO has a high holding torque and less hunting when stopped, so the text is captured by the camera even in a short pitch motion. Since the AC servo generates the minimum torque when stopped, hunting occurs. And you can see that AC servo cannot capture a text in a short pitch motion. However, you can see that the text is captured only when you move the beginning and end. That is, a long pitch. To explain more about the belt pulley system, due to the mechanism structure, the belt pulley is a single pitch motion from the motor shaft perspective. For example, in the case of a ball screw, when the lead is 10 mm, the motor moves only 10 mm in one turn, but in the case of the belt pulley, when the radius is 10 mm, when the motor turns once, the belt moves 62.8 mm as you can see. I will show you a demonstration of the belt pulley in action. If you look at this part, you can see the short pitch motion of the motor in the belt pulley demonstration. You can see that the word "no hunting" is accurately captured without hunting even in a short pitch motion. In summary, in the case of an AC servo, the position error decreases when decelerating from the target position, and the motor torque decreases when the position error decreases. Near the target position, the torque generated by the AC servo is very small, and the belt is of low rigidity, so when the belt is shaking, the force is transmitted directly to the motor shaft, so it continuously affects the shaft. On the other hand, in the case of a stepping motor, as the speed decreases, the stepping motor increases the torque and produces a maximum torque near the speed zero, near the target position. So, in the case of AC servo, since the torque is small near the target position, it is difficult to stop without hunting because the vibration caused by the tension of the belt is directly transmitted to the motor shaft. The stepping motor can overcome the vibration and stop without hunting without a gearbox. Because the torque generated by the stepping motor at that time is relatively larger than that of the AC servo even when the vibration caused by the belt tension is transmitted. I'll use a video of the wafer transfer robot as an example. As you can see, the WTR has a belt pulley structure inside. In the case of belt drive, the moving distance is long, so many people think that it is a long pitch motion that moves a large distance from a motor standpoint. However, from the motor standpoint, it is a short pitch motion due to its mechanical structure. As you can see, the distance the object moves seems to be long, but you can see that the motor does not turn even a single turn. This is an example showing that a stepping motor can be applied to such a WTR. The next video is about delta robot. In general, AC servo motors are used a lot for delta robots. However, when a AC servo motor is used, the torque at stop is small, so most of the motors are driven by installing a gearbox. In the case of stepping motors, the robot can be connected directly to the motor shaft without a gearbox because it generates the maximum force when stopped. If you look at the actual motor drive, it is a short pitch motion. It is a good example that a stepping motor can be applied because it repeats stopping and driving. This is a demonstration of a Delta robot from Aigüs, Germany. This Delta robot has a belt pulley structure and is a short pitch motion from the perspective of the motor shaft due to its structure. You can see that the motor does not rotate 180 degrees. The stepping motor does not need a gearbox because it operates in a low speed range with short pitch motion. If you use an AC servo here, you may need to attach a gearbox when stopping. The following is a demonstration showing a high-speed short-pitch motion using two motors. A disc with 8 small grooves was attached to the two motor shafts, and the grooves were vertically engaged. You can see the grooves interlock without collision while the two motors alternately driving in high-speed short-pitch motion. This operation is possible because of the precise position control through the high-resolution encoder of the Ezi-SERVO and the characteristics of the stepping motor without hunting after stopping. Let's summarize what we have looked at so far. FASTECH Ezi-SERVO has 3 advantages by adding high positioning accuracy to the two factors that it can reduce the settling time. Due to the high holding torque characteristic of the stepping motor, so there is no tremor or hunting after stopping, and there is less overshoot than the AC servo. In the Korean market, it was possible for FASTECH to move the closed-loop stepping motor market from here to here. It also replaced AC servo market, especially 100-watt and 200-watt class AC servos. It wasn't easy. This is because customers' perception of AC servos and stepping motors was so strong. However, after the customer felt or actually experienced the advantage of Ezi-SERVO, it was possible to replace it, and now many customers use Ezi-SERVO. From now on, I will introduce the actual application example of Ezi-SERVO. Prior to introducing application examples, the main factors that could be applied Ezi-SERVO are as follows: position accuracy, lost motion, overshoot and robustness. High position accuracy, low lost motion, small overshoot and robustness as stop at the target position without hunting after stopping. Based on these 4 factors, I will not introduce how Ezi-SERVO could be applied to each application by replacing AC servo. The following is the LC dispensing machine. LC means liquid crystal. 2 glasses are needed to make LCD panels used for this TV and monitor. It is the TFT panel on the left and the color filter on the right. A certain amount of liquid crystal is dropped on the TFT panel as shown in the picture. Glue is applied to the color filter as shown in the picture. And then, the part where the liquid crystal is dropped on this panel is bonded to the color filter on the right. When bonded together, the TFT is this part, the color filter is this part, and this is the glue, and this red part is the liquid crystal. And when it is bonded, this liquid crystal spreads quickly. For example, when you press the panel with your hand on the TV, that is, when you press the liquid crystal, the pressed part is changed color. The reason the color changes is that the liquid crystal is liquid, so when it is pressed, the liquid crystal escapes to the other side and the amount of liquid crystal changes in the pressed part, causing the color to change. For this liquid crystal volume to be constant, this drop must be constant. In other words, it is a very important process that determines the quality of the color of the LCD panel depending on how precisely and uniformly, or quantitatively, this liquid crystal is dispensed. Therefore, the 32,000 ppr encoder, which has the highest precision in Ezi-SERVO, is also applied to this machine to increase the precision of liquid crystal dispensing. In addition, in order to bond the panel and the color filter, the glue must be uniformly applied to the color filter. If this glue is applied more on one side and less on one side, as you can see, the applied part is not straight, it is applied like a snake. In this case, the area on which the liquid crystal is placed changes. The amount changes when the area changes, and the color changes when the amount changes. In other words, constant liquid crystal dispensing and uniform application of glue are key to improving the color quality of LCD. From the conclusion, in the past, customer used a AC servo when dispensing this liquid crystal. In order to drop this liquid crystal, from the perspective of the motor shaft, it is necessary to move to a high-speed short pitch. However, if you use a AC servo at this time, there is a high possibility of overshoot. Due to the overshoot, the amount of liquid crystal was not dispensed uniformly, and the engineer was forced to tune the gain every time, and the cumbersome and laborious work continued. However, if you use FASTECH Ezi-SERVO, of course, the stepping motor will overshoot, but the amount is less than that of the AC servo. Also, no gain tuning is required. On the other hand, since the amount of AC servo is not constant and varies depending on the gain tuning, we propose to apply the Ezi-SERVO. But because of the customer's general perception that it also could not be a stepping motor when the AC servo was not available, it took a year to suggest and do a test for replacing from AC servo to Ezi-SERVO. This is the actual liquid crystal dispensing machine. It took a year to get the opportunity to test the Ezi-SERVO. But after the engineers actually tested the Ezi-SERVO, the AC servo that was on the entire machine could be replaced with the Ezi-SERVO at once. I explained earlier that the glue must be applied to the color filter regularly. In this case, it is necessary to use a laser sensor to control the gap between the panel and the dispensing to be constant. This machine shown in the picture is the machine that controls the gap between the nozzle and the panel through a laser sensor. In order to dispense a certain amount, the distance between the color filter and the nozzle must always be constant. In other words, since gap control to keep the distance between the nozzle and the panel constant is necessary, an expensive laser sensor is applied to this part. The color filter looks flat on the surface, but is curved. Nozzle must maintain the height between the bented color filter, and apply the glue following the gap. That gap is 50 microns. For example, if the distance between the nozzle and the panel is 100 microns apart, you have to move 50 microns at a time. If this spacing is not constant, such as 50 microns, if the distance is far apart, the glue will be less applied. Or it will be more applied if applied closer. This means that the distance between the nozzle and the panel is always constant in order to apply this glue evenly. For example, if your goal is to keep a gap of 50 microns, if the nozzle is 60 microns away, you'll have to order 10 microns down. When commanded like this, the Ezi-SERVO goes exactly 10 microns. Also, if you are 40 microns apart, you need to change the direction of the motor because you have to up 10 microns. Even at this time, the Ezi-SERVO moves up to exactly 10 microns. In the case of AC servos, of course, position accuracy and lost motion are good, but the possibility of overshoot is high. So if an overshoot occurs and the motor moves too much, the glue may not be applied evenly. There is even a risk of damaging expensive panels by contacting the nozzles and panels. The graph you see is the measurement of the response of the AC servo and the stepping motor when the AC servo and the stepping motor do up and down by 10 microns under the same conditions. As before, the nozzle was not gap controlled by following the distance from the panel. But this time, 10 microns were only up and down in a fixed position to see the difference in response between the AC servo and the stepping motor. If you look at the graph, the red graph is AC servo. In the same case of 10 micron up and down operation, the AC servo up and down 3 times at the same time. Of course, there is gain tuning, but if you increase the gain, there is a possibility that the glass may be damaged due to overshoot. In order for the servo to move without overshoot, the gain cannot be raised, which will result in a slow response, so it is not possible to quickly up and down. In comparison, Ezi-SERVO up and down 9 times without overshoot at the same time. If you use Ezi-SERVO, it means that the speed of the machine is calculated to increase 3 times. For example, if the speed at which the glue is dispensed is 100 mm per second, it will move 100 mm for 1 second. And if you use a AC servo, the gap control, that is, up and down, is done 3 times. So the point to be corrected will be once every 33.3 mm. However, since Ezi-SERVO does this up-down motion for 9 times at the same time, it will add 3 times even between 33.3 mm. If the AC servo is used even within the same 100 mm, due to the response which eliminates the overshoot, the late response will be calibrated sparsely as before. If there is another bent point of the glass in between, the response will be slower to compensate for the gap. So, what's happening if you increase the speed by 300 mm per second, that is, triple the dispensing speed? Because Ezi-SERVO does up and down 9 times, as a result, it will correct the position same as the AC servo did 3 times. This means that the machine speed is tripled. In other words, by changing one motor, it has tripled the speed of the machine, increasing actual machine productivity by 3 times. In other words, there are many machines where Ezi-SERVO can perform higher than AC servo if the motor is well selected according to the machine. I will introduce a small actuator as the next application example. In the case of small actuators, there are many high-speed short-pitch motions that move short distances at high speed, which is the advantage of stepping motors. And it is sufficient to apply Ezi-SERVOs instead of AC servos. So, it is an effective market for cost-effectiveness. As previously shown, in the case of a small actuator, all the torque of the AC servo cannot be used because the moving distance is short. And it is an application that can take advantage of a stepping motor with no hunting characteristics at the target position. Therefore, in the past, mostly AC servos were used, but many customers who know the advantages of stepping motors use Ezi-SERVO. Lastly, I will show you examples that Ezi-SERVO actually applied to a small precision stage, replacing other companies' closed-loop stepping motor. This is Japan's Suruga Seiki Konyo stage used for camera module alignment equipment. You can see that Ezi-SERVO is applied. In addition to Japanese stages, you can see that Ezi-SERVO has been applied to the Mentor stage, a Korean small precision stage company. You can see that FASTECH's Ezi-SERVO motor is applied to Taiwan's small precision stage. On the FASTECH website www.fastech-motions.com, you can download product-related materials such as catalogs, manuals, drawings, and watch demonstration videos and webinars. Also, if you search FASTECH on YouTube, You can see about more than 100 demonstration and webinar videos. Thank you for listening.